Welcome to this first tutorial in the series of motor protection tutorials. Today we're going to see and learn a bit about the device selection for motor protection and the main protection tasks. My name is Michaela Mönikes. Sometimes I'm a tour guide on the Siemens booth during exhibitions, and today I'm your webinar guide through this webinar or through this tutorial. So what's up on today's agenda? What can you expect from us today? We will start with an overview of motors and protection devices, and you will get a glimpse into short circuit protection. The webinar will then continue with CT dimensioning and the configuration in Dixie. And last but not least, you will see the thermal overload protection and its configuration in Dixie. And as you might already know, it's not me that will present all these interesting topics, but I have an expert here with me in the studio. My dear colleague Klaus Wagner will share his knowledge on motor protection. He's definitely a passionate protection engineer and an experienced technical consultant for transformer, generator, and motor protection. And the best thing around Klaus is that he will share his huge knowledge with us here. So enjoy the webinar, place your questions into the questions to the speaker tool, and then you get the exclusive chance to ask Klaus directly. Okay. Almost directly, because you type the question and I will read the question at the end of each presentation block and ask our expert. So make use of this possibility. And now, Klaus, please share your knowledge on motor protection with us.
Okay, I will do. Thank you, Michaela. Yeah, also hello and welcome to this webinar. Now the prompter is missing today.
Oh, I'm sorry.
Before it was too often there in the screen, now it was missing. I took one slide with the prompter, not the whole presentation, but it's a little bit easier to start off. And now I can read hello and welcome to this tutorial also from my side. My name is Klaus Wagner and I'm the Product Lifecycle Manager for Motor Protection in the CProtect 5 relays. In this tutorial, we would like to present and discuss the motor protection functions of CProtect 5 in detail. We've planned in total 2 sessions. In the first session today, we will talk about various aspects of short circuit protection and the thermal overload protection for the stator. In the second session, coming on the 2nd of May 2023, we are going through all aspects of thermal protection of the rotor and also show you additional functions and handling features. Finally, we would like to go through the complete configuration of one specific application example for motor protection and discuss its settings. For this tutorial today, we planned 3 parts with a short break in between them. In the first part, after the introduction, we talk about short circuit protection possibilities for motors. Thereafter, I will show you how to select and correctly dimension the current transformers, and we will go through Dixie, where I show you how to set up the configuration for the discussed relays and protection functions. In the third part of today's tutorial, we explain the thermal model, which is the basis for our thermal overload protection function for the stator and also for the rotor, and explore the features of these functions and its settings. So let's get ready. Enjoy the show. Basically, I would like to start with a short overview of the motor. So we have typically 2 motors we protect with our CProtect 5 relays. The one is the induction motor or asynchronous motor, and the other one, the synchronous motor. So for the asynchronous motor or induction motor, we have a stator, what you see here on the right-hand side, with 3 windings for the 3 phases, and they are ordered or applied in a symmetrical way, as you can see here. And I have a sine curve voltage on each of these phases, and they induce me a current, and this current creates a field here, and each of these windings create me a dynamic field, so a sine curve, an alternating field, and the combination of all three fields gives me a rotating magnetic field here with a constant amplitude, but this is rotating with the frequency of the grid, so the connected voltages here. Then, as a second part, we have the rotor as such. The rotor in an induction or asynchronous motor very often is, as we see it here, a closed cage, so with bars here and then rings at the end to make a short circuit of all these bars. This is also called a squirrel cage. And yeah, this is, let's say, one of the most common part of rotors with some other type, and this is the wound rotor with slip rings. So instead of having here bars, we have really windings on this rotor, so either two-phase or three-phase windings, which are brought outside and outside onto slip rings. And here we can put a resistor at the end of this winding, so to increase the resistance of this winding. This has one dedicated effect, and the effect is that during startup, I increase the torque of this motor or rotor. So wound rotor as a second way of construction, basically. So we find those two here mainly. The principle now is the following. I have this rotating field of the stator. The rotor itself is unpowered. So as you already saw, there is no current which is injected. It's just a short-circuited cage here in that case. And what now happens is that the magnetic field of the stator rotates over the rotor, induces a voltage in the rotor bars, and there comes then a current as a consequence. And due to the Lenz rule, we can say the rotor tries to compensate that. So it starts to rotate to decrease the speed of the field that rotates over the rotor. So the rotor is accelerated and then runs at the end and drives then the connected machine on the motor. Okay, so the frequency of the rotor depends basically on two facts. One fact is the number of pole pairs and the synchronous frequency. So this is the frequency we get from the grid, so the 50 or 60 hertz normally. And as I already mentioned, the number of pole pairs. So here in the stator, we see now just not even a pair. It's a simplified drawing here. So we see just one winding. Normally we say pole pair because we have a second winding, so that we get here a magnetic field all over the rotor, across the rotor. And if it's like that, that we have just these three windings for the three phases, then we say we have one pole pair. That means the rotating frequency of the rotor is approximately the synchronous frequency we get of the rotating magnetic field. And if we don't want this high speed, we can cut this down by applying more pole pairs here. Then with one rotation of the electrical field, or with one cycle, then this magnetic field does not rotate completely over the rotor, but only a fraction of that. So the rotor speed decreases by the number of pole pairs. We can basically say the synchronous frequency divided by the number of pole pairs gives me the frequency of the rotating magnetic field. The rotor as such, again, does not rotate exactly with that synchronous frequency. It rotates with a lower frequency because to drive the machine, it needs a field, a magnetic field rotating over the rotor to induce the voltage and the current. And with this current, we get the power to drive the machine. So the speed of the rotor is not as fast as the synchronous speed, it's below that speed. Therefore, it's also called induction motor or asynchronous motor. So the rotor is not synchronous with the magnetic field, but slower. So here we see a characteristic of the torque. So the y-axis is the torque, and here the x-axis is the speed, the rotation speed of the rotor. And we see typically when the motor is at still stand, here is 0, then I get a certain torque, and with the increasing rotation speed of the rotor, the torque goes up to a maximum value here. This is also called breakdown torque, and then goes down with a negative inclination here to the synchronous speed point. And as already mentioned, we do not reach that speed point normally because the rotor needs some power to drive its own or to compensate its own losses. And if there's a machine connected, then also to drive the machine, so the speed is slower. And now you see on this diagram, it's a kind of, how to say that, backward coupling. I don't know if this is the correct English word, doesn't come to my mind at the moment. If I need more power, then the rotor speed goes down, and with a lowering rotor speed, then the torque increases. So that means then I have more torque, and then I get a new stable point. So then basically we are working on this here part of the characteristic, depending on how much load is there on the motor and how much power the motor must deliver. And this game goes until to a certain point, and if the required torque or power is too big, then we move over this breakdown torque. And the name breakdown torque is exactly because then the whole system breaks down. If I'm here and the torque this motor can deliver is not enough, then the motor will slow down further, and with this further slowdown, the torque becomes lower, so there's no chance to come back, and the motor will go to standstill. On the right-hand side of this diagram here, you see there's written generating, so I can use that machine also as a generator, this principle. For this reason, or to have this, I must have a higher rotor speed than the network frequency. Then it's just the other way around. Then I push electrical power into the grid by the mechanical power which I apply here on the rotor. So you see it's a kind of symmetrical characteristic here of the torque. And as with the synchronous motor, also the asynchronous motor, basically the same principle can work also as a generator, what we see here on the right-hand side. We often encounter one value which is called the slip here. The slip, as you see in the formula, is the synchronous speed minus the rotor speed divided by the synchronous speed here. And you see when the motor is at still stand, then this rotor speed is 0, then the slip is 1. And if the rotor is running at the synchronous speed, then here the numerator is 0, so the slip is 0. And in case of a generator, the slip is negative. So you can encounter this this quantity all the time when you deal with motors technically. The power range of a motor, of an asynchronous motor, is roughly in the range as indicated here. It's more a guideline. It's not that we have a strict border here. I did not investigate complete grid internet to see if there is a motor manufacturer which has even bigger motors. So I think the majority will be in that range, even lower than 25 megawatt normally. Okay, the difference, we have synchronous motors. Also there we have a stator with the 3-phase windings distributed across the whole stator here. Here's just one winding indicated, so you need to add the other windings for the other phases here. And also these windings create this rotating field of the stator, which goes through the rotor. Now the rotor here, in that case, is not powerless, let's say. So there is a power going in. We have a DC current on this rotor because we have a winding in the rotor, and here we inject a DC current. So in reality, it's a DC current with a lot of ripples, but the important part is the DC current, which creates us also a permanent, more or less constant magnetic field, which goes here through the rotor. So the principle now is the following, that the rotor follows the stator, so the magnetic field of the stator, synchronously. So there is not a slip, not a frequency difference, or an angle difference is there, but it's not a different speed. So the rotor really follows the field, and what is the other regulation quantity? If I need more active power, then the angle between the rotor and the magnetic field of the stator increases. So let's say the current in the rotor always gets a force created by the magnetic field of the stator, which always shifts the rotor in the direction of the magnetic field. So it keeps pace and it moves synchronously here. This is the difference. Also here I can overdo the situation. If I need too much power, then the angle becomes bigger than a certain value. And then the rotor falls out of synchronism. So then the whole thing becomes asynchronous. And for the synchronous machines, this is not a good state. So in that case, normally you switch off the motor. Also here, for the rotating frequency, the speed depends on the synchronous network frequency, basically, and also on the number of pole pairs. The more pole pairs we have, the slower is the rotor. Here we see an example of a salient pole machine. So salient pole because we have here these noses, and here we have the windings around these noses. And the more noses we have, poles or pole pairs, the slower is the frequency. And also here the rotor frequency is just the synchronous frequency divided by the number of pole pairs. And here, this is exactly the value when they are in synchronism, because the rotor is as fast as the magnetic field that rotates around. Okay, number of pole pairs, this was already discussed. So the power range here, again, don't really take this as a strict range. This is what I found more or less. We have here power range from maybe 1 MVA until 1 megawatt, until 50 megawatt or even bigger. Later I show you a picture. You will see a picture of a machine which has, according to the documentation, 65 megawatts. Okay, let's have a look on what C-Protect 5 offers as motor protection relays. I made a subdivision in 3 categories. Also here, that is not really a strict separation. It's more kind of guideline, what we find in the market or with our customers, with the applications, what is installed for which motor. Yeah, the small motors, if we would like to call them like that. For this, we have just a current input, so current transformer, and we evaluate everything with these currents here. So for this setup, we have as the smallest candidate, the 7SX800. This is our C-Protect 5 compact relay. And SX means it's a universal relay, kind of universal relay. So this is not a dedicated motor protection relay, but it is a relay which you can apply also for the standard overcurrent protection function, for motor protection. Even there are some functions for capacitor bank protection inside and many other functions. So basically everything that fits somehow to this hardware setup. So what is special to this relay is that it is small, so not large, but small in that dimension, in that direction here. And with this, we have, as a consequence, a limited number of IOs, inputs, outputs. The next bigger, let's say, class of protection relay is the 7SK82. This is a dedicated motor protection relay. And also here we have universal relays in our C-Protect 5 range. They are called 7SX. So we have here also the 7SX82. So what is special for this relay is that it is like the base unit of a modular C-Protect 5 relay, but it's not expandable. So you cannot add expansion modules. For the rest, for the motor protection, for all the relays I present you here, we have always the possibility to load the same functions into the relay. The difference here is mainly the hardware setup. Optionally, of course, we can use our bigger devices, the 7SK85 or 7SX85. These are modular C-Protect 5 relays. And yeah, also here we have a universal relay, which we can use to load almost any application or protection function into this device here. So the smallest range where we just have the current measurement. Then for the medium part here, the medium-sized motors, we have here additionally a voltage input. And yeah, it's very simple. All the relays I showed have also the option to accommodate a voltage input. So then we can, here for the motor protection, mainly it's the undervoltage protection. We can run the undervoltage protection on top of the rest of the protection functions here. And if we come to the bigger motors, to the larger motors, additionally, we maybe want to apply a differential protection. You see here is a second current transformer on the star point side. And for this, we cannot use the smaller devices like SX800 or 7SX82, SK82, because they have just one current input. Whereas the modular devices, as you might know from the C-Protect 5 range, there's the possibility to add expansion modules, as we can see here. And these expansion modules can have also current inputs. So with such a setup, then I can host the two current inputs here in one relay and make a classical differential protection on top of the voltage input or whatever is there additionally. Good. So these devices are dedicated for asynchronous motors. We have another range of devices, and now you see we have a overlapping here of functions. Originally, we said for this synchronous motor, we have a dedicated device, the 7UM85, which is originally this C-Protect 5 device for generator protection. So generators normally are the bigger ones, synchronous generators, and we have there also functions for a synchronous generator and motor implemented in the 7UM85. This is namely the under excitation protection, maybe the out of step protection, rotor ground fault protection, just to name the most important of these functions here. Meanwhile, and therefore we added here also the other devices, we have these functions also available in the 7SK85. The rotor ground fault is missing there still, but in the SX85 I can have the same functional setup as the 7UM85. So also for the synchronous motors, we can choose one of these device types, and basically you're free to select what you want. SX maybe is interesting if you want to standardize your device family, then you have just the 7SX85, maybe a 7SX82. And with these devices, we can cover basically all protection functions, which we can also have in our family bound devices, so the motor protection, overcurrent protection, and so on. Okay, here additionally, the possibility to add more hardware for the second current transformer, and then we can make a differential protection. Let's come to a little bit special thing, and this is these ATEX certificates. ATEX is French and stands for Atmosphère Explosive, so explosive atmospheres, environments. And there we have only a limited range of devices which have this ATEX certificate. So on the one hand, we have the 7SK80. 7SK80 does not belong to the C-Protect 5 family. It's the predecessor, let's say, of the 7SX800. For this, we have this ATEX certificate, and you see it's a dedicated motor protection here. Then in the C-Protect 5 range, we have the 7SK82, the non-modular device, and finally also the modular devices, the 7SK85 and the 7UM85. Why do we have these limits? Simply because these ATEX certificates, there is a certain effort behind, and this effort regards the firmware of the device and the hardware of the device. So we need to qualify or guarantee and prove also versus the certifying institute. We need to guarantee and prove that we have a certain minimum range or minimum value of outages, failures of the relay. This is basically the main topic here. And this proving has some effort on our side and also on the certification institute side. So basically this costs money, and therefore we cannot do this for every dedicated protection device, firmware and hardware. And therefore these variants are special ordering variants, just to point it out once again. And we have a dedicated firmware which has this ATEX certificate and a dedicated hardware setup. So this is especially for our modular devices. That means you cannot just select whatever you like as a hardware setup. You have to choose out of a certain range or group of devices. So we made some setups from just a smaller device to a bigger one with more IOs, for which we calculated these failure probabilities and for which we then started to prove that we fulfill all these ATEX requirements. Basically, what is behind this SIL level 1, which we must fulfill. And in this SIL level 1, there's a certain number of or rate of outages or device failures, which we must fulfill. The devices as such are not different to the CPROTEC 5 devices as a standard. It's just that we picked out that we selected a certain firmware and a certain range of hardware for the qualification. Therefore, we have these dedicated devices. And so you cannot just take a device and upgrade a firmware, then you lose the ATEX certification, or the device you have does not have this ATEX certification anymore with a new firmware. And also if you change the hardware setup, and it's a hardware setup we have not tested and calculated and proved, then you're also falling out of that ATEX certification range. Therefore, you must just take the device as you can order it as a fixed box in that case. Although it's very interesting often to modify the hardware. And we have a dedicated manual that comes along with each of these devices, where there are some special measures described what you need to do so that you can run these devices under this ATEX qualification. Good, let's have a look on the protection functions and on the type of faults, or the other way around, type of faults and which protection functions we have for that. First, we have short circuits in the motor, 2 or 3 phase, and here we can apply a overcurrent protection function or also a differential protection. Then we have earth faults or single phase to ground faults in the motor. Here we have typical earth fault protection or ground fault protection functions. And we must differ here between grounded networks and basically isolated or compensated networks. For the grounded networks, the standard overcurrent function will do. For the isolated and compensated networks, we have dedicated special protection functions for that situation. And they are very similar or identical, I would say, to what we encounter in medium voltage grids in the distribution area here in Central Europe. We have very often these Peterson coil grounded networks, and also there we use dedicated sensitive directional ground fault protection. Thermal overload of the stator. This is mainly during the normal operation a problem. So the normal operation stresses the stator. The startup stresses the rotor of the motor more. And here we have a dedicated function, and we will talk about this function later. Then for the rotor as such, we can have different problems. The one is the start is too long because the load is too big, the voltage on the motor is too low. And this is a thermal function against a too long start of the motor. The second problem can be that the startup is too frequent in a certain time range. For this, we have another function, the restart inhibit function. And the next problem for the motor is the loss of phase or the negative sequence current on the rotor. The rotor is very sensitive against that. And for this, we have also a thermal function based on the unbalanced load current, let's say like that. Of course, we have also a non-thermal one, a classical negative sequence. This could be used to detect if one phase is completely lost, because then I get a relatively big share of negative sequence current, and then I don't need to think about thermal effects, then I just can trip the motor. Okay, increased load situation. So you have a working machine and something blocks in there, and then suddenly the load current jumps up. For this, we have a so-called load jump protection, and this is basically an overcurrent protection function. Then under voltage protection for the situation when the voltage is too low, just to prevent a too long start If I know I cannot start up, then I can stop that right at the beginning. And for this, I have, for example, the under voltage protection function. Overheating of plant or unloaded drives. This is more protection of the working machine, which is behind the motor. And we can detect the situation looking at the current. If the current is lower than normally, whatever is normal, then we can give an alarm or trip the motor, because then we can conclude probably there is no load on the machine. Bearing overload, so if the bearing heats up, this we cannot detect via measuring the current, but we can apply temperature sensors there at the bearings. This is normally done, and bring these temperature sensors to our C-Protect relays and give an alarm if the temperature is too high, so we can integrate these temperature sensors. And then for the synchronous motor, finally, we have some special functions like the under-excitation protection, out-of-step protection, rotor ground fault protection, and maybe a couple of others. Yeah, that's, let's say, the range of protection functions we offer. The first three I will discuss in this session, and the majority of the rest of the functions will come then in the second session. As I already mentioned, I think it's the 2nd of May when we have this second seminar or webinar tutorial. Good. Now let's approach step by step to the protection functions finally. So here we see a motor start current, an example, and we see typically three things. The first thing is we have a peak here at the beginning, a kind of inrush current, and then we get the relatively constant current during the startup phase. So this can also, can also moderately slowly change the amplitude. Some low frequency can be also in there, which we don't find in this example here. But basically the amplitude here, the RMS value is more or less constant. It can also decrease slightly. And at the very end, when the motor has almost finished the operating speed, then the startup current goes down and I get here the load current at the end. And the size of the load current mainly depends on what load is connected to the motor. That means the bigger the load, the bigger is the current. That's clear. Whereas for the starting current does not really depend so much on the load which is behind the motor on the machine. The load on the machine, on the motor, defines how long is the startup procedure. The bigger the load, the longer is the startup. But the amplitude of the starting current is more or less independently really of the load. And it depends on dimensioning factors of the motor, so how the motor was constructed basically. Okay, so we have to consider all these aspects because the motor is not just running, it's also starting up. And for all the cases, we need to be prepared with our protection function that we don't have an overfunction on the one hand and that we are not too insensitive on the other hand. And this brings me to this overview here with typical example values. So we have here again the starting part of the motor, the startup with this peak and then the starting phase, and then the current breaks down to a relatively low value, again depending on the load here. And I put in here some typical values. So the start current can be around 5 times nominal current of the motor. And the length, as already, no, we did not discuss about the length. So in the fault record here before, does this come back? We see this is a very fast startup, only a couple of seconds here. If the load is heavier and maybe the voltage is not the nominal voltage, then the startup procedure can also take 20, 30, 40 seconds, maybe longer, even a minute, in that range. So a couple of seconds until roughly to a minute, I think, will cover most of the situations for the length here for the startup procedure. Okay, how can we protect now this with an overcurrent protection function? First idea is to put an instantaneous stage over the maximum current which can occur here under the normal conditions. So I put here at, for example, 10 times nominal current a stage without delay, so an instantaneous stage. Then I can go here behind and say, okay, after this peak, I have a relatively constant starting current. So I will put here another stage, which I place with a certain margin above this startup current. However, I have to think about that here I need a time delay not to catch this peak current right at the beginning. So typical values here are roughly 100 milliseconds, 50 to 100 milliseconds. This you can test during the commissioning, however. How long is that peak? And then make your delay time of that stage here accordingly. And now, depending on how long is the startup, we can add also a third stage as a backup, which we can then bring down to a level which is above the maximum expectable load current here. However, the use or sense of such a stage, if the startup procedure is very long, is rather limited. So it is a kind of backup, but yeah, we can add it because we can do it with a numerical relays, but when this trips only after 20 seconds, so I don't know what is if this is really a reasonable thing, but we can do it and we have it. So why not apply it at that point with the limitations what we have? Then in this diagram, we have also curves from the thermal functions. They are more symbolically in here because this tripping time we get here depends on the preload mainly, how much load was there before, current before, and therefore it is not at a fixed value here. It depends on what has happened before. We see that later when we talk about these thermal protection functions. Finally, what we can do to improve this situation, I can apply this differential protection. And you see the sense of the differential protection. We are fast and we are sensitive because we don't care about the startup and the load current. This does not disturb us. We look at the differential current, and this is normally almost zero during the startup and the load situation. And therefore, I can be very sensitive. So you see here our standard value of 0.2 times nominal current, which is the classical value for a differential protection here. And then the load jam protection, you see this has a relatively short tripping time, and this would definitely interfere with the startup procedure. Therefore, this can be activated only, and it's activated by the relay when the motor is running. So we detect when the motor is starting and when the motor is running with our relay. And only when the motor is running, then we activate this load jam protection. Again, with a relatively short tripping time, that means if something happens, so either a fall with a small amplitude that we don't catch it with the other stage, or a load jam situation, then we can react on that in the range of seconds normally, then we can trip the motor, but we need to be sure that we are in the running state. Okay. Let's have a look how we can set the overcurrent protection. Basically, I already mentioned it. We have the 3 stages, or at least the first 2 stages are relevant. Instantaneous stage, and here a practical value is go 30% above that transient current. So to have enough margin here on that part here, so that we don't interfere with the startup current and we don't apply any time delay. So here we can trip immediately. If a current is big like that, it cannot be something regular, it must be a fault. Recommendation here is use the RMS values because we can have current transformer saturation that cuts off as a part of the current on the secondary side. And if we take this truncated current and put a filter on top of that, then we truncate this current even more. So the RMS value evaluation works against the saturation, and here it's a good way to use that RMS value evaluation. Then the second stage here, the high set stage, basically here we could recommend to set it to 20% over the maximum startup current. So consider here the maximum voltage you can get on the motor. So have this margin, and then also consider a time delay, so not to catch here that peak current at the beginning and trip on that. And then we can have this stage already relatively fast and active during the startup. However, the bad point is I must be over the start current. Here the recommendation is use fundamental values because these fundamental values reduces effects of the DC part of the currents. So we are closer to the sine curve value of that. So also here not to have an overfunction in that case that we, with the RMS method, we also evaluate the DC part here. So then we come a little bit closer to the characteristic here. Okay, and the delay time is already mentioned. You can check that during the commissioning. If you need more than 50 milliseconds, 100 milliseconds, whatever is the value, the time of these peaks here. Okay, and finally here, this relatively slow backup stage, if at all we can apply such a thing, then we need to be higher than the maximum load current here. Okay, that's how we can apply the overcurrent protection. Maybe a word to the ground fault protection in a grounded network. We can apply just ground overcurrent stage 51N. The setting here depends on what we encounter as a measurement error during the startup. So I would say, have a look. What is the ground current, apparent ground current, which you see in the relay when you start up the motor, and then put a threshold here with a big margin on top of that. So 10, 20% maybe. And then you have a relatively sensitive single phase fault protection additionally. For the compensated networks, it's a little bit more complex. I want to skip that point because there we need another maybe half an hour to discuss that in detail. Maybe we do that in another seminar. Okay, let's have a look on the motor differential protection. First of all, we have to think about a differential protection. Distinguishes internal and external faults, and especially for the external faults, we think about the region behind the object. So outside of these current transformers, internal means inside of the current transformers, external means normally, of course, also in front, but also behind. But if there's the power supply from the left, I will not see some current if there's a fault in front, because the fault current goes into the fault and I don't measure here much current on that side. The only exception is if the motor feeds back to that fault, if the motor is running, then I get also a short current going into that fault here in front of the motor. But basically we can say, if we have a fault here somewhere on the places 1, 2, 3, then we must anyhow trip the circuit breaker here on that place. So this doesn't make sense, or doesn't make sense to spend a lot of effort to understand, do we have an internal or external fault? So we have a little bit to go away from that concept here. Besides, the fault here on the position 3 will not be a fault really, because the cables here are anyhow short-circuited behind the motor. So if I have a short circuit here, I will not detect that with a relay. Okay, so this is what I already explained here. The purpose of the differential protection rather is to find faults, small fault amplitudes, when the motor is running or also during startup, and be much more sensitive than you ever could do with a classical overcurrent protection. Okay, and so the enemy, let's say, of the differential protection, which is normally the external fault, to be stable for external faults. Here the rule is to be stable during the startup phase of the motor and of course during the operation, but the startup phase is the critical part here. Disadvantage, now we talked about the advantage, is simply it costs more money, there is more effort, I need a second current transformer, I need the differential protection function and so on. So it's then again consideration, how much money I want to spend, how important is the motor, how important is the process which is behind. Definitely the differential protection is more sensitive, and there's also the chance to have a smaller damage on the motor, basically, because it detects currents before they really evolve to big currents. These currents are already seen when they start to evolve, and there we have maybe a time advantage also. So we could say as a tendency, I would expect that we have a smaller damage of the motor when we protect it with a differential protection. This is basically what is behind. Good. We have the classical principle of the motor differential protection, as you see here on the left-hand side. So I have a current transformer also on the start point side in the relay. Then I make the calculation of the differential protection here. The classical principle, we need three-phase current transformers additionally on the start point, and I do the calculation in the relay. We do this phase selectively for each phase. We compare the currents. With a second principle, and you see, additionally to the standard current transformer here on the in-feed, I have a second one, and this is so-called window type current transformer. What we see here in this picture is just one, but in reality we need one for each phase. And the idea is that I bring the current through the cable through this window type transformer, then it goes into the motor. And then before I form this start point, I go back through this window type current transformer and then make the start point here. So what happens in this current transformer is that the currents under normal conditions flow in both directions equally with the same amplitude, back and forth, and then they compensate each other magnetically because the magnetic field is resulting theoretically, ideally, is zero. In reality, it is not, but it is almost zero, so it is a relatively sensitive thing. And of course, under normal conditions during the startup, I will not see really a current flowing here. Okay. What I use as an evaluation, although it's a differential protection, is a simple overcurrent stage, because I need to see is there still some current available or not. If there's an internal fault, then I will see the current that flows into the fault, and the current back is not there because it's the internal fault. So there's a difference between both parts here, the feeding and the outgoing part of the cable. Whereas for a normal startup, both currents compensate each other mostly. Here additionally required is are three-phase current transformers and the differential protection function in the relay. Here we need additionally this window type current transformer, one per phase, so three in total. We need single phase cables, and we need to bring them back through this window type CT and make the start point here. So it's a little bit more wiring or mounting effort. As a difference, we have a simpler function. It's just an overcurrent protection function. So the pros and cons, I would say, are balanced out quite well. Therefore, we find both methods. I don't know, maybe in the past, I'm not old enough to judge about that, but maybe in the past it was easier to just apply an overcurrent protection function and use this window type current transformer. Nowadays, if we use here our differential protection function or the overcurrent protection function, the effort is not that big, or there's not a big difference at all. So the difference is maybe a little bit in the cost of the protection function and the additional wiring what we have here. So I would consider them more or less as equal here. Good. Let's have a short look on our motor differential protection function in our ZProtect 5 relays. First of all, we calculate the stabilizing current as you see it here on the slide. So I take the maximum current of all sides of all current transformers and not the sum as we did this in ZProtect 4, ZProtect 3 and others. And here we encounter basically the two principles for the stabilizing current. The one is the maximum of the currents, the other one is the sum of the currents. It's better to say the sum of the absolute values of all currents. There's a third option which makes the sum of the currents divided by 2. This is equivalent to the sum of the two currents. It's just weighted with another factor. So the principle is the same. And there is a third principle basically in the literature. We use that in kind of that way in our restricted earth fault or restricted ground fault function, just to mention that here a little bit. Under normal operation, the current that goes in is identical with the current that goes out. And we count all the currents that go into the object positive. Therefore, I2, which I measure here, is minus I1. You see this also in the fault record. You make a fault record and you have a look on both currents. They will be in counter phase. So for each phase, both sides will be in counter phase. Under normal operation or operating condition, the differential current hence is 0, and the stabilizing current is one of the two currents because they are more or less identical here. Then with this principle for internal short circuits fed from both sides, if both currents have the same amplitude, then it can happen that the differential current is twice as big as the stabilizing current. A little bit unusual. If you have the classical or the first method of the stabilizing currents in mind, there you cannot go over, the differential current cannot never be bigger than the stabilizing current. Here it is the case with that principle. However, for the motor protection, not, because we don't have an infeed from that side. Why I'm telling that? Because the motor protection function we use, the differential protection, is identical with or is based on the transformer differential protection. What we use is a subset of functionality and settings. All the settings which are not relevant for the motor, we just take out of the function and they are invisible. You don't need to care about that. But basically, the function itself is identical with the transformative protection. Therefore, I took also that slide from the transformative protection training here. For the internal short circuit fed from one side, then this side is 0, and the differential current is identical to the current that comes in here, and identical also to the stabilizing current. So this is basically how the principle is set up. When we talk about differential protection, we talk a lot about stabilization against external faults, so that I don't have an overfunction for external faults. In that case, for the motor protection, we can forget external faults and substitute that with the starting current. So we need to be stable during the startup of the motor because, as I already mentioned, we do not really have external faults. Okay, this is what we normally do. We have two cases: high current faults, where I have CT saturation relatively fast, and I can have also low current faults in some cases when the current transformer saturates because there's a lot of DC component in the current. And maybe again remnants in the current transformer, so then it tends, there might be the possibility that it jumps up just over that here, that relatively sensitive stage, only for a couple of samples and turns back, but this is enough to issue the tripping command. Therefore, two principles. This is a little bit text for, let's say, the documentation to read if you like. Basically, we have the two principles. What is relevant mainly is during the startup, I have more I would say the high currents, not faults, but startup currents. I mentioned already we use the same principle because it works fine for the motor protection. Therefore, we have here our classical characteristic with a threshold, a slope 1 and a slope 2 section. The slope 1 is to compensate for linear faults, and the slope 2 here is to compensate additionally current transformer saturation. For the current transformer saturation, we have additionally, let's say, we look at the trace of the trajectory. So this is the differential current, this is the stabilizing current or restraint current. Maybe I should say this before. And we have here in this green area a zone, and we know if we have a jump in the current, then this can be a fault. And if the current trajectory now here in that plane goes in this direction here, so it enters this field, then it looks like, yeah, for the other devices, like an external fault. Here it is, yeah, it looks like there's the starting current flowing in, flows out, and then a little bit error here. If we then suddenly go up here into the tripping area, so the gray part here, then we know, okay, we had an external fault or the starting condition of the motor maybe. And if now suddenly I jump up, then it's very likely that I have CT saturation and not an internal fault. So we have the possibility to block then the tripping for a certain time here. And yeah, this is how we make the additional stabilization against CT saturation. We see here the standard settings, and yeah, I also tell this when we talk about the transformers. Normally we can keep these standard settings. We tested these settings and made a lot of dynamic tests, also used yeah, fault records, for example, from the field, which we got from the field. And then we basically made these settings here, and you can take them over if you don't have better information. This would mean dynamic tests with a motor or something like that. So especially for the motor, I think it's rather uncritical. If you have other protected objects, then you could find here and there maybe some other values, but they work fine as a general statement here. Good. Startup recognition is a special function only for the motors, because there we have to deal with a long time elevated currents during the startup. So I said this can take seconds, 10 seconds, 20 seconds, and this could stress also current transformers. And we found here and there problems with the current transformers. So therefore we have the possibility of this startup recognition and to react when we see there's a startup of the motor. How does it work? I have here my classical or my standard characteristic. And what we can do is that we set a factor here to increase our threshold by this factor and to increase also the slope here of that characteristic. So then it's steeper, and we keep that characteristic until the motor has finished the startup, and then it drops off. So there's a time which you need to set, and you need to set this time bigger than the starting procedure of the motor here. Also here, think about motor start with a reduced voltage. Also this can happen, and the startup is longer, so you need to consider the worst case here. Okay, here's the text again, what I said about that. And now we come already to the question and answers. And let's see if you have already some questions. I think Michaela comes
yes,
with the questions. I make a little bit space here for the PC. And then
Thank
let's
you.
see.
And we do have questions.
Oh, a long one.
That's true, that's a long one. But we start with the first one, and that's a short one. Because NA wants to know, where will the second CT set be installed for the differential protection?
Okay, now the question is which type of the differential protection?
It was rather early during your presentation. So I think the question came in around the first 10 to 15 minutes.
Maybe it's already answered by the diff protection part, which I did. Basically, I have one current transformer upstream and one on the start point side of the motor. If it's a classical differential protection, if it's the window type CT, it must be, of course, upstream of the motor, because I need to get the current that comes in and compare it with the current that comes up. So I cannot compare both currents on the start point side. So the window type CT upstream, the second CT for the classical diff principle is then on the start point, as we saw.
Thanks. And then SL wants to know how quick the differential function will be picked up for internal motor fault. Hopefully in terms of milliseconds.
Yeah, in terms of milliseconds, but this depends here. We have two stages. I did not go into detail for the second stage. Here the recommendation is to put that stage over the startup count. This stage is trimmed to be fast. So a lot of additional functions to stabilize for the low threshold. What we have for the first stage is not there. So this is the fast stage. And I don't have the exact times in my mind now. For the normal stage, the sensitive stage, we have tripping times around 20 milliseconds maybe. Here you have to think about, if you think about transformer protection, we have to wait for the inrush current detection, for example. So we don't have this here, but we get tripping times around that. For the fast stage, maybe around 10 milliseconds. This depends also on the amplitude, how big is the current compared to the threshold again. You find these times in the manual at the end, so but it's in that range somewhere.
Thanks. Yeah, the next question is long, and I think it's interesting because it's describing that in the schematics we use, or SKG uses 3-phase, so 3 wires to the motor, and then it's kind of ending at the motor. Nothing's coming out. So how to, and we talk about those single lines, line diagrams, where we place just one line going, in some cases, even going through the motor. So we talk about CTs on both sides of the motor. Is it a short answer to tell SKG how to place the CTs on both sides of the motors, or will you do it at home as homework and write a dedicated answer there?
I think if you want to apply the differential protection, then you need to have access to the star point. So you need to measure the current behind the motor, outside of the motor, and compare the two currents. So if you have the star point somehow in the motor, you cannot make the differential protection. Then you have just the overcurrent protection. And you cannot do it even with a window type CT, because you need also then the current coming backwards and put it in counter direction in the Windows type CT at the end. So in that case, so for the differential protection, you really need to have access to the other part. So otherwise you cannot measure that current.
All right.
Somewhere.
So you need this line coming out of the motor, get access to the star point.
Somewhere you must have a current transformer there.
Yeah, that's true. So last question for this round. Can a motor protection be set up in a transformer differential CPROTEC 5 device?
Yes.
Oh, that was easy. That brings us to the first break.
Maybe one more word,
Okay.
Not just one word,
no problem.
a couple of sentences, a couple of more words. The transformative protection has the classical transformative protection, and there are also the options to load motor protection and generator protection inside. As I already mentioned, it is more or less the same function as the transformative protection function, but simplified because we need a couple of things not for the motor and generator. For example, vector group shift, zero sequence current elimination, that's all stuff only we encounter for the transformative protection. Inrush protection, for example, motor does not have really an inrush with the second harmonic. So that stuff is out and you don't have the settings. So these functions are also in the 7UT and in the 7UM, the generator protection device. We have also generator protection function and transformative protection function. So it's kind of overlapping what we have or what we offer as protection functions in our relays. And if you want to have the complete freedom, go for the 7SX85. There you can put in whatever you like, any combination.
Just by function points.
Yeah, exactly.
That's true. And we have another webinar on that. I know. All right, this webinar will continue after a short break. I think about 7 to 8 minutes will be fine. And give your eyes and your ears a bit of a rest. Have a sip of coffee or tea, whatever you need. And then let's meet again in a few seconds, minutes, I think.
Minutes, yeah.
Seconds will not be okay, so minutes.
Okay, then see you later, hopefully.
Stay tuned. And welcome back to the second session or second part of this first session in the tutorials around motor protection. And now you will learn a bit on CT dimensioning, and Klaus will share his knowledge on the configuration within Dixie. So let's continue the journey.
Yeah, okay, let's attack that point here. Yeah, CT dimensioning. So now we talked about the short circuit protection functions. The question is now, what current transformer do I need that this works in a proper way, so that the relay, that we can guarantee what is written in the manual as technical data, what the relay performs. And therefore, when we have a look in the manual, we see here, this is an extract of the manual. We have in the appendix always the requirements of our protection relays or functions for the current transformers. And we have here basically for the motor protection on the one hand, I put this a little bit on the side here, again, the overcurrent protection function and the differential protection function. And we see here for the various types of current transformer definitions, we have always here our requirements. And in the coming slides, I would like just to make an example and show you how this works. Okay. Gerd, can you take me out of the picture, please? It's a little bit disturbing or distracting, let's say. Okay, here is the example. So I have my circuit breaker, motor, here's some motor data, and this is my current transformer. And the relay here is relatively close to the circuit breaker, so in the same switch gear, and then I have the cable to the motor here. Okay. My required operational accuracy limit factor is this here, and we saw this in the formula we had before. So I will now go for the P10, P5, P current transformer definition first. Later, I have also an example with the knee point voltage and with the ANSI definition. Okay, so this is my requirement. Now the question is, what is the maximum threshold we have here? Yeah, we learned before I must put this instantaneous element over this peak of the starting current with a certain margin. So I need to have the starting current first, and the starting current I can calculate from the nominal current of the motor normally, or during the commissioning, I switch on the motor and see, okay, what is the current? And then I can adjust here the threshold and measure out what is the peak current here. So normally you get the nominal current of the motor from the manufacturer. If not, then you can calculate it also from the power and the voltage. So with that formula here, in our case, 107.8 amps. The starting current is, as a maximum, we can say 2 times so the transient starting current is as a maximum 2 times the steady state starting current, or the beginning starting current. you can take that, or if you have better information, then you can also say, okay, I can reduce that maybe because my peak is always much smaller than this value here. And here we have one given indication for the motor. My starting current here named with AM is 5 times the nominal current of the motor. So my transient starting current is as a maximum 10 times the nominal current of the motor. So I just need to multiply that number with factor 10. The threshold now as a practical value, we said, okay, let's put 30% on top of that. So times 1.3, then I come to this maximum threshold here. The IPR, the primary current of the current transformer here is 150 amps. So this is also given, and we now can calculate this ALF dash factor here. First, let's have a look on what we have now in this setup. So the rated burn of the current transformer is 5 ohms. If the current is 1 amp, then the ohm value is identical with the power in VA. There's just a difference. If the nominal current of the current transformer is 5 amps, then this value is 25 times smaller. So that means this current transformer can drive a load with 5 ohm behind, and then it will work as under nominal conditions, basically. Okay, the actual connected burden now is the sum of the resistance of the wiring and the burden we have inside the relay. Normally, the burden inside the relay is so small that you almost can neglect it. So this has not a real big influence, but the wiring normally, and we see that here. So here is a formula to calculate the resistance of a cable with a certain length and a certain cross section. And you can fill in here the values, and then we see I have 1 point. Okay, this is a very small cable, so we have almost the same dimension or range of ohm value here. So 0.17 ohm, and here it's 0.1 ohm. So you should not neglect this, but it plays a smaller role. Maybe I must correct myself here a little bit. So we get finally 0.27 ohms as a value for the connected burden. Okay, and then we can calculate the actual operational accuracy limit factor. So this is this ALF dash. This is the nominal value. So in that case, it will be the 10. It's the 10 after the P. So I remember that always thinking about, we have also 5P20 current transformers, and then the 5 is the accuracy, and the 20 is this ALF factor. So with 10P10, okay, it's both the same, but you don't know where is it, which number is at the end relevant. Okay, here we have a formula, classical formula, which you get when you consider the internal resistance of the current transformer and the connected rated and real burden, and you can get make a little bit calculation there, and then you get this formula. And normally the actual burden, the actual ALF, the ALF dash factor is bigger than the nominal one, because you normally put a smaller burden on the current transformer as the nominal burden is. And this is what we see here. So the RBC, the connected burden, is in the denominator here. So this quotient here becomes bigger than 1. And this is what we see here. So instead of 10, we get here an ALF dash of 40.1. Okay, but at least 20. So the required factor is at the end 20. So sorry, this is what we have. The required one is I need to divide now my setting value here, the 1400 amps by the 150 amps, the nominal current of the current transformer, and then we get 9.34. But it should be at least 20. This has again something to do with the remanence of the current transformers. Therefore, we normally want to have here a certain minimum value. In that case, the 20 is relevant, so it must be bigger than 20. And if we now compare what we really have, actually we have 40 and we need 20. So what we have is more than what we require. So everything is fine, the condition is fulfilled. We can say with this current transformer, we can make easily the protection of this motor here. Only a short word about the CT range. This has nothing to do with, or is not relevant in our case now for the overcurrent protection. Here the idea is to check in a second step, when I select a certain current transformer, does it really transmit to the secondary side? Or no, better, do I see in the relay with such a current transformer and the maximum fault current, do I really see the full curve? Or is there kind of clipping? Because if the secondary current is bigger than my measurement range, I will have a clipping. So then I see a sine curve, for example, but instead of having the tip, I see a part of the sine curve and then a flat part, and then it goes down because the ID converter does not go further. To do that, we need to know, okay, what is the biggest short circuit current which I can get here? And yeah, now we can calculate this in detail with a network calculation program, or if we have just a transformer, we can make a fast and rough estimation, and this comes here. So my short circuit current behind such a transformer, a power transformer, is the nominal current of the transformer divided by the short circuit voltage here, which has normally a value like between 5%, 15, 20%, so in that range. So if you don't know what USC means, it is this percent value at the transformer. And with that, we get an estimation. We estimate always a current which is bigger than in reality, because we do not consider any impedances upstream of the transformer, so we are always on the safe side. And here in our case, we see, okay, we have a maximum short circuit current of 61 times the nominal current of this current transformer. That means, if you think about the measurement range of our 782 relays as X or 7SK82, here the dynamic range goes to 50 times nominal current. So we will here see probably some clipping in the current, which does not play a role at all, because we talk here about overcurrent protection, and this clipping has no relevance because our threshold is at, where was it, 9 or something like that. So we will always get this current. For differential current, especially for a transformer, this different grade of clipping can be a problem. Therefore, I mentioned this here, because anyhow, we have different levels of current transformers, voltage levels, and nominal counts of the current transformer. So here you could have this problem. There you need to keep an eye on that. Another eye you should keep on the thermal capacity I have for the current inputs. This is normally no problem. We have enough range here, but it might happen if you get an enormous, tremendous secondary current, because you have a very small current transformer, that you theoretically get a current on the secondary side, on the input of the relay, which is much too big. So this is also a point where I would say it makes sense to keep an eye on that. Here for our motor protection, this has no relevance. I just wanted to point out this again. I just put it here because it fits into the complete range of considerations here. Even for the differential protection, if I use identical current transformers on both sides here, then they will have the clipping equally on both inputs. So the differential current still is roughly 0. So this does not have an effect either here for the differential protection. Just to mention that, to keep that aspect in mind, therefore I put it here. Okay, so what do we have here? Overcurrent protection. Now we come to the other transformers. We can have a class PX transformer. There we define the performance via a knee point voltage, and we also need to know the internal resistance of this current transformer. And we have a formula also here in the manual for the required knee point voltage. You see, there's always somewhere the ratio between the maximum threshold and the primary current of the current transformer, and then a little bit around that here, and also a fixed value, at least 16 times instead of 20. So it's basically the same requirement which stands behind, but expressed as a knee point voltage and not as an ALF factor here. Then we have the ANSI class current transformers. Here we have a so-called terminal voltage. Also for this we have a requirement which we formulate here. And also here we see the same, more or less the same requirement. We have a fixed value and this ratio here. So basically it's always the same principle what we have. Let's have a look. This maximum threshold current we calculated already to 1400 amps here. And we need to have a look on the connected burden again. So on the left-hand side, we have a 1 amp current transformer. So this remains identical. It's the identical values here. On the right-hand side, I wrote we have here a 5 amp current transformer. So the burden of the relay needs to be divided by 5 to the square. So I get here, in that case, a smaller burden. Okay, if we go to the knee point voltage, then we have here now now we can calculate our required knee point voltage, but just by inserting all the values in that formula, and you see we come to 9 volt, but at least 16 times that stuff, so we come to 25 volts. So in that case, the 25 volts win, and this is the requirement what we have. And on that side, the requirement is described in that formula here. So we insert here the values and we come to 9.8 volts and at least 20 times this here. So we come to 17 volts. So you see it's rather similar here, the values what we get out basically. Now we can make the comparison. We have the required knee point voltage and we have the knee point voltage given by the current transformer. So this is 100 volt. So this far away from the 25. So this current transformer will work fine. And I could also think about using a current transformer with a lower knee point voltage here. And for the ANSI, it's the same. So the required value is 17.4. And with this current transformer, I have a knee point voltage of 100 volt. So I'm also far away from the requirement. Also, those two will work. Let's have a look on the differential protection. So the other, let's say, basic requirement we have for the current transformers in motor protection. And there I took another example. And let's have a look on this current transformer here, because we need to select what kind of current transformer or the features of this current transformer now directly. Again, we need to look into the manual. The required operational accuracy limiting factor is now the starting current divided by the primary current times 4, the transient starting current divided by the primary current. So it's not a threshold, it's the real current. And also here, we say it must be at least 30 that we can securely use our sensitive threshold here. So we can say, okay, we can also use a weaker current transformer, but then we need to make a compromise and we need to raise our differential protection threshold. And this is not really what we want, because we want to measure relatively sensitive the currents here. Transient starting current, same story as before. I calculate here the nominal current and then have a look. What is given here, it is also 5 times the nominal current is the starting current. And if I don't have better figures, then I take 2. So this value here is between these values is the factor of 10. The requested factor is, so according to that formula, 13.3, so 7,580 divided by 1,000. So this is the current transformer here. So the result is 30.3, but at least 30. So in this example, this value here now wins. It's a little bit bigger. Now I can think, okay, what current transformer could I take here for that start point? First consideration, they should be identical more or less. So it is of advantage, or it does not have a disadvantage at all if they are identical. So I would go also for a 1000 amp to 1 amp current transformer. It's not a must condition, so it's not mandatory. You can have completely different current transformers as long as both of them fulfill these requirements. Everything is fine. This is what we tested and what we guarantee here. But to make things simpler, I would say it makes sense to take also a 1000 amp to 1 amp current transformer like this one here. A difference here is that I have here a relatively long line, a long wiring to the relay, because this is here in the field where the motor is. So therefore I said, okay, maybe let's take a nominal burden which is higher, 20 VA, instead of, what do we have here, 15 VA. Good. The burden is equivalent to 20 ohm, because it's a 1 amp current transformer. Now let's calculate the connected burden, the actual connected burden. It's again the same formula all the time, so we have just to throw in all the values here, and then we get as a result 1.5 ohm. Now you see in that case the burden of the wiring is much higher than the burden of the relay. This is what led me to the statement before. Normally the burden of the relay is relatively neglectable compared with the wiring burden here. This is what we normally have as a situation, that the wiring burden is higher than the relay's burden. But you should add it to be on the safe side anyhow. Okay, good. Now we do the game in the other way around. That means we now have the required ALF factor here, which is 30.3. I have already some characteristics defined, selected of this current transformer. What is missing is the number after the P. I want to know, do I need a 5P10 or 5P15 or 5P20? And therefore I just invert this calculation. It seems the same at the first glance, but if you have a closer look, then this quotient here is just capsized. So I have the connected burden here now in the numerator, and here in the denominator I have the nominal burden. So the value which comes out here is smaller than the required value, because we have again this underburdening. So the result is 7. Then I can easily say, okay, let's take 10. So I have a little bit margin here still in there. And then I come to a 1000 amp to 1 amp current transformer, 5P10, 20 VA. Now you see there we have a little bit a playground. We can also say, no, I don't want to use the 20 VA. I take 15 VAs, or I take another value, 10 VAs. Then as a result, probably this number here becomes bigger. Then I need not a 5P10, but maybe a 5P15 or 20. Everything is fine. This is because we have different levers for defining the performance of a current transformer. The one is this 10, 15, 20 after the P, so the ALF value. The other one is the power of the current transformer, the nominal burden of the current transformer. And the third lever would be also the primary current. So if it's a 2000 amp to 1 amp current transformer, then then the ratio here becomes smaller. So I need also then a lower factor. So these 3 levers, and we can play with that. As a tendency, I would rather go for a lower burden value and a higher ALF factor, because the calculation here we need to rely on the internal resistance of the current transformer here, this 4 ohm. And if I say I need 30 times nominal current and I don't need so much burden, then maybe the current transformer is more defined in that direction than saying I need the incredibly high burden and I don't care so much about the accuracy limiting factor. But again, as long as these requirements are fulfilled, everything is fine, and the current transformers can be also completely different theoretically. Good. This here I leave, let's say, for those who are interested. It's a little bit calculation again, and I think there is not so much new insight compared to what I already said. So you can go through that example and you will see also this current transformer will be okay for the differential protection. Now I would like to come to the Dixie, and I forgot, just a second. I forgot a sheet of paper which I need as a guideline for myself so that I don't miss any important point in the Dixie. So here it is. And then we can start. Okay. The Dixie is here, so I've already prepared a little bit something here, a project, and I would like to explain you let's say the basic steps, what to do in the Dixie for those who are not really familiar with that program. And we have also looked where we make the settings. Okay, let's first start. I have here a SX800 as the smallest of our motor protection members. And if I go here into the device information, for example, I get here some information of the device, and I open that because I need here this MLFB, because I would like to show you that at the beginning of each project, I have to add the device as such. So every device in the field has one configuration here in the project. This is the way how it should be used, the Dixie. And therefore, I create here a device. So either I have this product code on the device, printed on the device when the device is already there, or I can also get this in an online configurator. I think there we have also some webinars about that, how to use this online configurator. It's basically a guided tour through all the options, and at the end, there falls out a product code, which you can use here then to create a device. So in the Dixie, we click here on Verify. And then the Dixie offers us here various so-called application templates. And since this is a universal device, not a dedicated motor protection device, we have here applications for a simple overcurrent protection without and with voltage, a directional overcurrent for a grounded system, for a resonant grounded Peterson coil or isolated system. And we see here also two application templates for the motor protection, the one with the voltage and the other one just with currents and voltages and just currents. What is that application template? It's just a predefined bundle of functions, we can say, which we already created, which you can consider as a starting base, and then you can add or delete functions, whatever you want or don't need. Okay, I don't do that here because I have here my 7SX800 already. Before we have a look on the functions, maybe a few words about the function points. It's a new concept we have introduced with the CPROTEC 5 relays. Instead of ordering additional functions, which you could do with CPROTEC 4, there we had software options or functional options, often as a bundle of functions, which you then could buy together with the basic functionality of a CPROTEC 4 or CPROTEC 3 relay, for example. Here we have a different method. Here we buy the relay, or you buy the relay with a certain number of function points. This is a kind of credit you have, like a prepaid card on the telephone with a mobile phone maybe. So you pay a certain amount of money, and then you have this money on the prepaid card, and then you are free to use that amount of money on your prepaid card for whatever telephone call. So it's not important who you phone to. You have just paid the money, and here it is the same. So the amount of cash you have on the prepaid card is the function points, and how you use the function points you define later during the configuration, and this gives you the incredible flexibility that you can swap, change, erase, add functions. You just need to see that the number of function points is not exceeded. So much more flexible than buying a relay with a certain bundle of functions, and then you find out during a project, oh, function is missing, but the functions which are inside I don't really need. So with CPROTEC 4, you got stuck here and you needed to do some extra stuff. Here, it's not a deal as long as you have enough function points here. Basically, you can also upgrade a relay with function points. You can buy them later. You can buy them with a special online tool. You create an account. This is our function point manager. And then from this function point account or pool you have there, you can just create a file with function points which you download into the relay. In that way, in a couple of, I would say, minutes maximum, you can upgrade the functionality of a relay, and the whole system keeps you very, very flexible. Okay, enough about that. We don't make a webinar about function points, but I think this is one of the basic points which I wanted just to mention. We have here this enormous flexibility. If we have a look on the hardware here, hardware and protocols, for our compact relay, we cannot expand the hardware. Here, what we can do is I click here on my communication interface to, well, my PC is a little bit slow now. It's late in the afternoon. Here in the properties, I can define the properties of these interfaces. And if I go to communication, for example, it really is slow. It shows there is the 61850 protocol already selected. I can select other protocols for the SCADA. I can define the redundancy concept. For those who know that, you see here the options, RSTP. Line mode means a point-to-point connection to two different switches, for example. And then we have the seamless redundancy protocols in each CPROTEC 5 device, PRP and HSR, just to mention that. And we have other options here to define. So this is the editor to define the communication. And for the non-limited relays, for the modular devices where I can add hardware, this is the editor where I add expansion modules here, basically. Good. Measuring points routing. Here I define what type of current connection I have here. For example, 3-phase plus IN. There's also the option just to connect 3-phase currents or even 2 phases plus 2-phase current transformers. And then maybe IN separate. Then I leave open one input. So depending on this connection type, the relay knows and the protection functions know what is on each current input available. What is the meaning of that current that is there? Okay, and the same for the voltages. So here we have 3-phase to ground voltages assigned. Good. If I open the settings here quickly, now we come more to the settings. Then we see here, I have here dedicated folders, and these folders we call function groups. Each function group is a container. If I open now this motor protection folder, for example, is a container for protection functions that belong to that container, and every container or function group normally describes a certain object on the primary side. So like the motor here or the circuit breaker. If we think about a line protection, we have a function group line. This contains then all the protection functions that protect this line and so on. So with that container principle, we make a good order in the relay structure, and this order can be highly adapted to what we find on the primary side. So if we have 2 circuit breakers, for example, for transformative protection, or 3 or 4 or 5, whatever, we add just a number of circuit breaker function groups, and then we adapt to the topology here. Just to give you one example, here it's not that dramatic. Normally here we have one function group motor and we have a circuit breaker, and that's it, like for simple overcurrent protection which protects one line. Good. So this is the concept of the function groups, and now here we find our protection functions. Now finally we come to these protection functions. But before we have a look here, I would like to show you 2 more things because this is better in the logical order. Under power system, we have here our measuring points, the currents and the voltages, and here we make the settings. So here is the nominal current primary secondary for the current input, for this current input, and further down we find also some supervision functions that are related to this current input. And the same we have for the voltage inputs, basically. We do not have a dedicated 1 amp or 5 amp relay. It's just a changeover of the settings here in the Dixie. That's all you need to do. So if you have somewhere 1 amp and somewhere 5 amp current transformers, you don't need to have different CPROTEC 5 relays on stock. It's always the same device, and you just make a setting here, and you don't need to open the relay. It's just the setting. Don't need to open the relay and reset jumpers or something like that, because we don't want you to open the relay. Okay, and the same we find here for the voltage inputs. Now you see I adapted this to a motor with 6.3 kilovolt, and 100 volt is the secondary voltage or whatever you have on your current transformer here. Voltage transformer, sorry. Good. If we go here into the general part of the motor function group, then we have here settings, and these are the rated values of the motor where all the protection functions refer to. And I put it in a way that I have a 1 megavolt amp power motor, so apparent power 1 MVA, and I get it with 6.3 kilovolt and 91.6 amps as a nominal current here, basically. Okay, now let's come back to the overcurrent protection function. Basically here, as a standard, we have 2 stages, and two stages are already available, created here. And I could use the 2 stages as we did before. You see, I did this already before. So I selected here RMS value. You have to switch on the stage. And here I selected a fundamental component. Here I have the delay time for the to overcome the peak, the inrush peak at the beginning of the starting current. Here I have no delay time at all. And the principle of C-Protect 5 is that I can flexibly add stages if I like. So now I added already before one more stage, this definite time stage. I could continue here, add one more stage, one inverse time stage, until to a certain maximum number. This is the flexibility we have. And if we don't need a stage, I just delete this stage here. So also here we have just a big flexibility. And I don't know what is the maximum number of overcurrent stages for the basic function, maybe 4, and we have an advanced function there. We have some more stages, so there is enough material to play. I would like to just show one thing. I would like to show you how to add one function, and I picked out here the breaker failure protection. So I have to go here to the function group circuit breaker, and here on the right-hand side, I have a big library of all protection devices. And I open here this universal, the compact device, and I go to the folder with the circuit breaker. And here is the breaker failure protection in that folder. And this is the symbol for this function. And if I want to add this function now, I just drag and drop it here onto the circuit breaker. And then you see this function here is available. And here are the relative settings. So you see, in that relatively simple way, we can customize our functions. And in the same way, I just delete that function again here. In that way, I can also delete the functions. And if a function costs function points, which I add, then I need these function points. If I delete this function, I get back the function points. And I can use these function points then for other functions, for example. So this is basically the principle how to work with DIC-5, a very rough overview, I would say. For the end, I would like to show you a little bit how we do this with a window type current transformer and maybe with a classical differential protection. Therefore, I would like to switch over to the window type current transformer. And let's have a look on the hardware first. So I added here an expansion module. I can get it here from a catalog, and I just drag and drop it here with another current transformer, because I need a separate input for this window type current transformer. And I can place it here or here, it doesn't matter. This is just how I make the assignment internally. Good. To be mentioned, maybe to be kept in mind, what comes from this window type current transformer, so the overcurrent protection that works on that, must be different or is different and works only on that current and is completely different or separate from the other current transformer and all the standard protection functions like the overload protection. Therefore, I need to have a separate box where I put this overcurrent function in. And this separate box we see here in the settings, I created another function group or container, which we call voltage current 3-phase, or this is a standard universal function group, and here I put in an overcurrent protection function. And now this overcurrent protection function I can now set, let's say, for this differential protection function. How to set that stage, maybe a word in the same range of sensitivity as the classical differential protection, so at a relatively low value. You can test this also during the motor startup. Then you can have a look in the fault record and see what measurement errors are produced, how big is the apparent differential current in reality there isn't, and then put a good margin on top of that. So you come also to values like 10, 20% of the nominal currents should be fine here. Okay, so that's how to set this stage here. The connection now, how does this current go to this container and to this function here, basically is done in the function group connections. And we see here our measuring points, and you see here this is the second one, so the second current input. And this is now assigned here to this function group voltage current three-phase. So we have the three steps. On the one hand, if I go to the measuring points routing, I have here additionally on the second current transformer input my measuring point 2. And here we have the measuring point 2, which is connected with the function group voltage current three-phase. And in this, I have this protection function, which I can now design for the differential protection at the end. Yeah, that's a little bit the structure. There is more behind, more flexibility, but I think this gives you already a taste or an idea what you can do with C-Protect 5 relays. And I once was asked the question, can we protect also more than one motor with one C-Protect 5 relay? Now, I think you know already the answer. It is yes, because for each current transformer we just need to add the proper hardware, and then we add here the functions, and then I have individually customized functions for each motor. And I can add more than 2 motor protection functions or schemes inside 3, 4, 5. The exact limit I need to check, but I think at least 5 is possible. I know for the classical overcurrent protection, we can at least protect 10 feeders with overcurrent, directional overcurrent, auto reclosure, synchro check, I don't know, but breaker failure protection. So not only just a very basic setup, but already a relatively big scope, this times 10. I think the limit is 12, but I don't remember exactly. And in a similar way, I think this could be possible also for motors. So just to show you a little bit the power we have with C-Protect 5 relays. Finally, one word about the classical differential protection. I've prepared one slide. Here, the setup is a little bit different. I have a function group motor stator. Here's the current on the in-feed side of the motor, and I have a motor side function group. Here I put the current on the start point side. And both go into a function group motor diff. And here are the differential protection functions, the real differential protection functions now, not the overcurrent protection. Here the real differential functions running, and this goes then to the circuit breaker. Also, very quickly, just a look on that, and then I think we can leave that part here. Here the structure with the function group connection is interesting. First of all, if I open the settings again, you see I have a motor stator. There are all the classical motor protection functions. Then I have a motor side. There is no additional protection function, and both bring the current to this motor differential protection function group. And here is the motor differential protection function running. And basically the structure I see here on the third tab. So I have the 2 sides, and the 2 sides feed the currents to the motor differential protection function. And I can also multiply that structure. If I want to protect the second motor again, then I just multiply that structure, copy, paste, and then I have 2 differential protection functions for 2 different motors. You see, it's a modular principle. It's very flexible. And this is the power we have here with the C-Protect 5 relay. So we can do almost everything what you can imagine. I would never say everything because we have also limits, but you see already the large variability we have here. Good, so this was it for the motor differential protection. Maybe one more word about the settings. And then I think we have mastered that. So I have here the sensitive stage, the IDIF stage. I need to switch it on. And then we find here the operate curve. So here I said we can basically take over these values. Then I have the starting detection. We can also take over these values. The only thing is that I need to enter here the maximum startup time of the motor, because for that time I have this less sensitive characteristic, and after that time I fall back to the sensitive characteristic here. So here you need to enter your maximum startup time. Think about a reduced voltage startup. This can take longer, so you need to take here the longer time. And then we have here the fast stage. I did not talk so much about the fast stage. Our recommendation is for the threshold, put it over the maximum starting time current. So this permanent starting current, not that peak. So this will handle the peak, but put it over the startup time, the starting current, this longer current, which we have during the startup phase, and switch this function on. And then we have here the complete differential protection as well. Okay, so this is not a profound training of all the tiny features to understand all the points here. There is just not the time for that. But I hope that I could give you at least the idea, the philosophy, what is behind, and also the impression that we can really adapt to a lot of different situations we have for the protection of our of your motors. Yeah. Okay, what's going on here? Okay, I'm here. Okay, so we finished, concluded the second part. Now, if there are some questions, it's time to see if I can answer your questions.
It's not a question of if there are questions.
Okay.
It's more a bit of if we have time, but we take some time, and we
pick
hope
out
that
some.
you will stay with us. No, I will not kick out questions, because all of the questions that you will not answer right now, you will get homework.
No, I need to
Yeah.
answer them later,
Yes.
but I will do that.
But that's the good thing for you. Each question you placed will receive an answer. If not now in this live version, you will receive the answer in a written format. And yes, the access to the presentation and the recording will be sent out to you, just to get this answer before I even place the question. And then, as I wanted to know, for overcurrent protection, the I greater set according the load current. And if the load changes dramatically, how can I define this I greater?
The threshold. So I said this before, you can put this as a backup function, so you have a relative stability, because you have normally a very long delay time, and it is not really a very good principle, I would say, but just to add it and say, okay, we can continue that scheme. If you have regular current, let's say, so your load, which is there, does not vary tremendously, and you don't expect that you get a jump in the load, which is really double current or something like that, 3 times the nominal current, that you could go for such a stage. In the other case, if you really have changing currents and you can have problems with the load that the current jumps up, for this we have a dedicated load jam protection function, which I will explain in the next seminar, in the next session in May. So please wait for that.
Stay tuned.
It fits there. So the invitation to come back.
All right, thanks. And then we take one or more questions right now in the audible way. The next one is the differential setting recommended the same as classical differential and the one with the line brought back. Okay.
Approximately, yes, I would say.
Okay.
I think the scope here is not to squeeze out the most possible sensitivity, because you always sacrifice a little bit the stability. And if you set this threshold too low, you might get influences due to the measuring error. So I would say a threshold of 0.2, what we have as a standard threshold, is good, because if you detect these faults normally become bigger. So it's not the point to detect 0.001 or so like that. 0.2 is below the nominal current, and this is the scope. As I said before, you can make several startups of the motor and see if you have this window type CT, what is the resulting measuring error. You will get a little bit of current, couple of percent, I guess. This depends on what does this depend? I don't know. How the cables are in this window type CT, and maybe also the window type CT has some errors. So you will find here maybe a small current, and then put your threshold above this current, so 100% over that. So if it's 5%, take 10%. If you see a current of 10%, take 20%. You have enough margin then to these measurement errors. And for the classical diff, I would say 0.2 is a good point here.
All right, thanks. We take one last question before we go into a little break. How is the startup curve set on graph from protection point of view? And will one SC before starting OC will trip first, or the startup protection will give command to the circuit breaker? Now that's a lot of abbreviation. Sorry for
I don't know what SC means.
Yeah, I have the same problem. We take that question offline.
Yeah, I think we answered this.
I think we will get this contact directly. So do not mind if you get a direct mail from Klaus. It might be the answer to your question, or at least a request
give me the
back to
information
your
what you
answer.
mean with SC, then maybe I can answer it.
All right.
I don't have an idea at the moment.
I think we are already running out of time, but not running out of topics. So I hope that you still stay with us. Nevertheless, let's do a short break. I think about 7 minutes will be fine again. And then you'll see the countdown, the timer going into the last round of, and now I need to peek into my agenda. What can you expect from us? Oh, that was interesting in the morning. I remember that. The thermal overload protection. And so stay tuned. See you in a few minutes.
Okay, see you. Stehst in der Zielscheibe.
And back again for the last part of today's tutorial around the motor protection. And I think you hopefully remembered that before the break I mentioned thermal overload protection. And now Klaus will share his knowledge on thermal overload protection on motors with you. Klaus, there you go.
Okay, yeah. So welcome back. And let's have a look on the third topic, overload protection, which is prepared here. So I have basically two parts. One part is to explain the theory and the thermal model we have, because this is the thermal model we have for all our overload protection functions for the stator and for the rotor. And yeah, then talk a little bit about the settings and some special aspects here. Okay. Gerd, can you take me out of the picture, please? So it's better for me. I missed something. This is my pointer here. Yeah, overload protection. This is now related to the stator first. It's a standard topic what we are discussing. So we apply the same function also for transformers. You can use that for cables, for generators, for motors, for all kinds of objects which can heat up too much. Okay, let's go for the basics here. First of all, thermal overload in a motor, I already mentioned that, is on the one hand for the stator. Stator is critical during normal operation, so already a small amount of overcurrent leads to a higher temperature or to a too high temperature. Whereas the rotor under normal conditions is when it's running, when the motor is running, is not stressed thermally. So here the thermal load is relatively low. But the rotor is stressed when the motor is started up because we get relatively high starting currents, and this is what the rotor brings to its limit. And here we have, I've already mentioned that, on the one hand, a too long start or locked rotor situation. I can have too many starts, or too frequent starts, and I can have problems with negative sequence current in the rotor coming from unsymmetrical or complete loss of one phase of the voltages. And we can have an overheating of the bearings. This we cannot directly monitor with a measured current. For this, we need a temperature sensor at the bearings, which we can also include in our motor protection function. Okay, basically, if I put some power into an object, here it is the PPL, power loss. The power loss is equivalent to the square of the currents times the resistances I have in that current path. So basically, the current that goes into the stator in our motor, the windings have a resistance. I have a resistance inside that represents the iron losses. All that contributes to the power losses. So the motor heats up when a current flows in. The bigger part, however, goes onto the working machine as a mechanical power, of course, but there is a rest, and this heats up the motor here. High temperatures directly do not damage the motor, but they stress the insulation material, and this goes on the lifetime of the motor. The higher the over temperature, the faster is the damage, or the point where you have a damage reached. So therefore, we need to control that thoroughly here. I put in power via the electrical power, but on the other hand, after some time, if I put the current into the motor, I will have a kind of stable situation, because there's also some power going out of this motor. And this is what we see here as a PCV convection power. So the power that flows out of the motor because of a temperature difference to the ambience. And here we call that convection because often there is an air stream inside the motor that brings out the temperature of the motor, so ventilation here. And in a steady state situation, the power that goes out is identical with the power that I bring into the motor that heats up the motor. So I have a temperature difference at the end. Okay, now it becomes a little bit complex. Therefore, this skidding symbol here with a car. We talk about the differential equation, and I bring just a theory which is behind this overload protection function, so that those who are interested can understand this, can follow then the single steps, maybe not today immediately, but when you sit down, I think the steps are so fine that you can follow that if you take you some time. For those who are not so familiar with the maths and the theory, don't get worried too much. There is a conclusion at the end, and as often with protection functions, the thing that is behind the protection function is relatively complicated. What you need to do with the settings is rather simple, because the relay takes over a lot of calculation and calculation at the end. Okay, so we work with a thermal model. It's a single body model, and this is also described here in an IC standard here, which you see on the left-hand side. And if you know some elements of the electrical circuits, then you will recognize here these elements, which we have also for the thermal model. Only with the difference that instead of a current source, I have here a power instead of a real electrical capacitor. I have a thermal capacitor, and instead of an electrical resistor in ohm, I have a thermal resistance here in Kelvin divided by watt. And instead of a voltage source, I have a temperature difference, a delta temperature here. And with that, you can apply the same rules as you know from the electrical model here, but just with these quantities at the end. And this is what we do basically to describe our temperature situation in the motor. We have to say that this is a simplification, this model. The motor has a lot of more complex structure, let's call it like that. I do not have just a block of iron and one temperature source, and then this block of iron distributes the heat outside into the ambience. No, I have the windings, which are copper windings. They are connected or they are close to the iron of the stator. I have a coupling to the rotor. I have currents in the rotor. I have a ventilation, and I have the iron that goes outside. So there are more influences to describe this motor temperature in a more precise way. So why do we use such a simple model? Simply for one reason, because we don't get the proper data if we would take a more sophisticated model. The data we get from the motor manufacturer is rather limited. So we try to find a model, or we found a model here. Therefore, it's also in this IC standard here. It's common practice. So we have this thermal model, this relatively simple thermal model, because it's a good approximation to everything that runs or takes place in the motor or the transformer or the cable. And we have the proper input data. This is the point, the proper input data which we get from the motor manufacturer that we can deal with this model. That's the reason why we don't have a model with a lot of bodies and a lot of resistances here and so on. We use just this here. Okay, this said, let's have a look what we can do. Of course, we don't get this data here, temperature difference and the power and thermal resistance of the motor towards the ambience from the motor manufacturer. We can expect to get a maximum current which we can put into the motor so that it does not overheat. And we get also time constant, so how fast the motor heats up. And that's basically all. And the nominal current maybe, this we also get from the motor manufacturer. So it's a rather poor input. And now we need to model or to derive something from this physical model here so that we can use it for our protection function. And we do this in several steps. And the first step is we describe this model here with an equation, and we have here a differential equation with the given values here. You can find them here in the equivalent model. Now here we have all real quantities like the power, a thermal capacitance, a thermal resistance. So we need somehow to get rid of that stuff and come from this physical model to something where we can use the data we get from the motor manufacturer. And we do this in a couple of steps, which I show you now here. So the first is we bring this differential equation to a dimensionless differential equation. So we try to normalize that. And for this, we have first a look on the steady state condition. The steady state condition is without this derivative here, so just the part here behind. And this is, let's say, what we saw before. I have a certain power that I bring into that body here. And then I have basically temperature difference and thermal resistance, and everything is stable. So here I have a certain temperature difference according to this base temperature. So we have here a reference temperature, this θ0, which is 40 degrees Celsius. Okay, the value which we use to make this standardization is the maximum power which I can bring into that motor if the ambient temperature, the surrounding temperature, is equivalent to our reference temperature here of 40 degrees. So θA is equal to θ0 here. And now I just divide this differential equation by this value here, and then you see I get all dimensionless values here. And this is the trick basically. So I scale my maximum, my power which goes into the relay, into the motor with an absolute maximum power, which I can have here. Okay, so still the skidding symbol here. We are not yet through. It remains a little bit with a lot of formulas. So this is what we had before. And now we introduce some abbreviations. So we have a thermal time constant. This is what we normally get from the motor manufacturer. Fine. So here, if you multiply that with the units, you see this is a time that comes out. Comes a time that comes out. Okay, then I have here a normalized temperature, the capital theta here, and the theta A capital for the ambient temperature here. Okay, if we have a look on the ratio of the powers, you remember maybe for the power is equivalent to the square of the current times the resistance here. So the ratio of these powers is equivalent to the ratio of the square of the currents here. And its maximum current normally I get from the motor manufacturer in the way that it is a factor K times nominal current. So I normally get the K times nominal current is the maximum current which I can put into the motor under the reference condition, so 40 degrees. And additionally, I introduce here a J to make an abbreviation of that fraction here, or quotient. Good. Then dimensionless, now our normalized differential equation is this here, or written also with a K here, I over KIN square is equal to this J square, and the rest is just what we found out by the standardization of the physical differential equation using the maximum power here. Okay, this differential equation has a solution, recipe, you can look this up, and you find this gives an E function. I wrote it also in a different way with this J here. So this is equivalent, and I call this here theta 2, and you see we have a theta 1. What is behind? If you put in values into this differential equation, you find out that you start with a certain temperature. This is the temperature when the time t is 0. Then you have a certain temperature here, and you reach a certain second temperature, the end temperature, after a certain time. Theoretically, you never reach that temperature because it's an E function, but practically after a couple of taus, you are very, very close to this end value. So this is the characteristic of such an E function here. And if the end temperature is bigger than the starting temperature, then I have an E function that goes up, and we can have the same also the way down. So if the starting temperature is higher than the end temperature, then the temperature falls down here. This would be the case when you switch on the motor and the motor runs up, and then it's running and the temperature goes up. And this is when you switch off the motor, then the temperature goes down because there's no current flowing anymore. Okay, so, and this is basically what is behind here. These calculations, as I already said, it's way much less complicated when it comes to the settings of that function, because we have just two settings which we consider, the K factor and this tau, the time constant, which we also get normally from the motor manufacturer, or I show you later a trick how to come to this tau. Okay, summary. If the current is K times IN, I reach the maximum temperature, and this is 1. So I get here an absolute value, and this is 1. If the ambient temperature is not additionally here, otherwise this also plays a role. As you see here, that I need to add this ambient temperature. This can be a negative or a positive value. Okay, what else? All values are dimensionless values, so therefore my maximum temperature is 1 and not a degree value, what you see in the relay. You see just the number 1, or we express it in percent, 80%, 90%, 100% trip. And yeah, to define the behavior, as I already mentioned, I need the nominal current, I need the K factor, K times IN is the maximum permissible current at reference temperatures, and the thermal time constant. The time constant you see also here in this E function. The time constant is bigger then the E function will start here and end at the same level of the temperature, but it will be slower because the time constant, you can construct it here in the way I did it here. So this is then the tau again. You take here the inclination and you go until to the end temperature. And this point is again the time constant. So if the time constant is bigger, then you stretch here the curve and then it takes a longer time until you reach the end temperature at the end. What is the sense of all that? We get a permanent thermal image. That means as soon as there is a current, we calculate a temperature in the relay. And the temperature is the one which we assume to be also the medium temperature with our approximations and simplifications in the motor stator in that case here. That means we trace the temperature all the time. And if we have already, let's say, a level where we almost are at the maximum temperature, and then we get a higher current, we have a relatively short tripping time because the motor is already loaded with the temperature, whereas the thermal model without memory, so here we talk with memory, without memory is then that I just do not consider the preconditions, what is before my overload condition. And this makes the things relatively wrong if you have already a relatively high temperature. So it is then giving us an underfunction. Here not, that's the big advantage we have. Let's have a look on the tripping time. If I have a constant current, we can calculate this. This is just the formula we had before, and the tripping condition is 1. The tripping temperature here is 1, and then we can solve that here. That equation, you see here's a logarithm inside. Now we need to understand what is theta 2 and theta 1 expressed in the current which we bring in, because we want to know what is the behavior when we put in a certain current. So the starting condition is I have a certain preload condition to the square plus a certain ambient temperature here. And this must be then a steady state situation. And I get a certain temperature with a certain steady state preload current. And now I have suddenly another current, a current jump. Then I will get a second temperature here depending on the higher current or lower current plus the ambient temperature, and all put together then I get this formula here with a tripping time. I can simplify that. If my ambient temperature is the reference temperature, then this theta A goes out. And if I say I want to start from 0, then I do not consider here the preload. So the formula again gets a little bit simpler at the end. Good. We can estimate the time constant. Normally you get it from the motor manufacturer. If not, then you might get maybe one pair of values as overload current and the maximum time you can put in the overload current if the motor is cold. So if it stands still and it has the ambient temperature. The K factor we get, again, we need that setting or this information. It's the maximum permissible current forever divided by the nominal current here. And from the tripping time without preload, I take this formula. Now I set in this TOL, this overload time, and here I set in the current here, IOL. And with that, solving that equation, then I get the tau, the time constant out of that. And you see it's also here a formula with a logarithm in the denominator here at the end. Here I put an example. I just skip over that for the time reason we have here. A couple of words to the temperature curve as such. Two things which I think should be mentioned. The temperature at nominal current conditions is 1 divided by k square. Why? Because it's that formula that is the basis for everything. And if I put in here IN, then it's 1 over k square here basically. The temperature for the tripping condition is always 1 here, and this would be then k square theta n. That means if we now take typical k factors for motors, this is 1.1 or 1.05, then you see for 1.1 our temperature is 83%. So it is much lower as you would expect, maybe, if you don't think about the square ratio here. And if it is smaller, then we have here 0.91%. So we are rather close to the maximum current, which is expressed in a rather small K factor. It's just a little bit above 1. To the curve, maybe another finding here. For a certain current which I bring in, here I get a certain tripping time as a multiple of the time constant. So this is a fixed value, and I put down here this table because maybe sometimes it could be useful. This means if I put 1.258 times k times in, so 1 divided by k times in, then I will trip in a time which is equivalent to the time constant. If I add, on the other hand, a current which is 10 times as big as k times in, I will trip always in 1% value of the time constant, so 100th of the time constant. And this is a fixed ratio, and this helps us sometimes to understand where's the temperature curve going to. I can also test this. Then I inject, for example, I don't know, 10 times nominal current or 3 times nominal current here. Then I need to expect the tripping after 10% of tau. And this is rather practical because if the tau is relatively long, then I can cut off my testing time. So instead of injecting 1.5 times current and waiting for 20 minutes, then I get here maybe in 90 seconds the result when I use that. Just to mention, I think this is a nice handy thing which I put here on the slide. Here, if I have preload, then you see here the tripping time is faster because I have a higher starting base. The curves all go to the same end temperature, but here the temperature difference is smaller. And this is the big advantage when I use this thermal model with the preload calculation, what we always do here, because we don't have the other principle anymore. Good. Let's consider now the ambient temperature measurement or estimation of the ambient temperature and how this has an influence on our settings. I just go and show here the formula. You can trace that. Basically, what we find is if this is our K factor for the reference situation, then I can get another K factor A for another ambient temperature. So ambient temperature now is different to the reference temperature. And then I get here this relation via this root here, and here is the theta A inside here. Okay, what does this tell us? With a lower ambient temperature, I get the possibility to put in a higher maximum current into the motor and also the other way around. So if my theta A is smaller than 0, this is the relative value, so the ambient temperature is smaller than the reference temperature. My Ka factor is bigger than the reference K, and in that case, it is smaller. Short example here. I made here a calculation. You can follow that if you like later. You need here one absolute value, the maximum temperature, because this is all with relative values, and we canceled out here the absolute values by making the reference considering the reference temperature. Here now we have another temperature, so here we need the absolute temperature to make that calculation of the theta A here. As you see, not on that slide, maybe on one of the previous slides here. And in that way, I can calculate now a K factor, for example, for an ambient temperature of 20 degrees instead of 40 degrees. So the question is, do I need to do that? No, because if we have this situation and you know your motor will never reach the 40 degrees and you will profit from this additional temperature margin, then you can use the K factor for 40 degrees. And then we have a setting called default temperature, and you set this default temperature to the 20 degrees Celsius here. And so you can leave the original K factor. The other possibility is to recalculate the K factor as we did here and set here 40 degrees, which is then a little bit unlogic because in reality you have 20 degrees but basically you keep the reference temperature and recalculate the K factor. But I would not recommend that. Take your reference K factor and set here another default temperature, and the relay will consider this. This is called default temperature. In reality, it describes the ambient temperature. And it's called default temperature because there's also a second possibility. I can adapt dynamically the thermal capacity or the thermal capability of the motor depending on the ambient temperature when I use a sensor and I measure the ambient temperature. Then I need to integrate that sensor in the calculation. This we can do. And now, if the sensor is broken, then the relay needs to know, okay, what shall I take now as an ambient temperature if I cannot get it from the sensor anymore? And then it goes back to the default temperature in case the last measured temperature is lower than the default temperature here, the setting default temperature, then it will go to that value. If the last measured value of the sensor is higher, then it will take and keep that value. So we go always into the direction of a higher reliability. So not to make an underfunction, not to let the motor run into a too high temperature. So we go on the safe side, in other words. Okay, then recently I had an example where we got the data for the motor, the K factor, but this was referring to 50 degrees and not to the 40 degrees. And then the question is, what can we do now? And on top of that, the maximum ambient temperature was 55 degrees Celsius instead of 50 degrees or 40 degrees. So everything mixed up. And we had to sort this out. And this I do here on the slide for you. We do the same trick. So these are the formulas you know already from the slide before. And now we say, okay, the 50 degrees, this is where I got the K factor for, is my reference temperature. Now I calculate what is my K factor for 40 degrees because this is the reference temperature for our relay as such. And this is, again, the same formula. So you put in the values and then you see what is under the root is bigger than 1.1. So the K factor here for 40 degrees is bigger, of course, than the one for 50 degrees. Okay, then I take that K factor and set it in the relay. And now when my ambient temperature is again different, I just set here the ambient temperature, so the 55 degrees. Then I have a K factor for 40 degrees. And tell the relay, no, the ambient temperature is 55 degrees, and the relay makes this calculation the correct way. So this is one way to set the relay. I found out, again, two other relays. I don't want to explain them here. They are equivalent. You get different temperatures, relative temperatures, different end temperatures. Even the interesting thing is the tripping time is identical from each preload situation. So I would say, basically, we have I found at least three different principles of setting this situation. I choose this one to present because I think this is the most logical one. You set the K factor for 40 degrees. You need to calculate that. And then you set the ambient temperature accordingly. What is the maximum temperature? Or you set here then the temperature sensor, include that. And then the relay will make dynamically the calculations, what is allowed or not allowed. Good. Here's an example. I run out of time, not only a little bit, unfortunately. Sorry for that. I planned to have it in a different way, but it turned out that I wanted to say so many things. So sorry for that. Here you can trace this calculation here. And basically, what is the outcoming? I have three relevant settings. I set the K factor, which I calculate before. So here the 1.1 comes out. I set a default temperature of 55 degrees when this is my maximum ambient temperature. And what I need is an absolute value. In this case, it's the temperature at rise at I rated. So the temperature difference when you have a nominal current flowing into the motor. This we have as a setting. This setting is often, let's say, makes some questions by the users. This is needed only if my default temperature is different to 40 degrees, or if I use a sensor, then I need this value here. And here's the formula how to come to that from the maximum temperature, or the other way around. If you have this value, you come to the maximum temperature by the formulas which you find in these slides. Okay, finally, one word about the temperature classes. So if you don't have a K factor, often you have the information from the motor manufacturer. The motor is dimensioned for a maximum temperature of the class F. And if we have a look here, we see this is equivalent to 155 degrees Celsius, and it's operated, so the under nominal conditions with a nominal current, it's the class B, so I have here 130 degrees. So now I have two temperature values, and from these two temperature values, I can calculate a K factor also following just these formulas here. This is what we know already. And where's the formula I wanted to have here? This one, this was on one of the previous slides. So the theta n is 1 divided by K square. And here you see I enter the values which I get from the absolute values. And with that, I can calculate the K factor at the end. So also here an orientation, if you don't have the K factor, if you have the temperature classes and you know what is the temperature under nominal condition, what is the maximum temperature, you can calculate the K factor out of that, as you can see here. In this case, I would set a K factor of 1.1. This is a standard value, it's a practical value, and it corresponds if your maximum temperature is 150 instead of 155 degrees. So you have a little bit more margin in there here. And then you have a kind of standard practical value here. Good. This is the list of the settings. We have a lot of settings here. The basic settings, again, is the K factor. It is the time constant and the nominal current, of course. What we have additionally is a time constant when the motor is at standstill. If there's no ventilation, then the cooling time is much slower. So I can set here another value. And if you don't have anything, take 7. So factor 7 to the time constant for the cooling. So this is a practical value here. And I have a current to say when do I reach this standstill. This is this current here. So if the current is smaller than, I don't know, secondary 0.1 amps, then you could say the motor is more or less at standstill, it's not running with that current. I have warning thresholds, a current and a temperature warning threshold, a drop-off threshold. So you see this is all a little bit additional stuff to the core functionality which we discussed. Here's one point which is important. If the device is powered off, should it keep the thermal image or not? I recommend set it to on. Then it keeps the last calculated value. So if you say here yes, and if the power comes back, then it starts with that value. So you have rather a too sensitive setting or too sensitive situation. If the relay is powered off for a long time, then it will also clear that memory. After 500 seconds, we reset that value, because then we say, okay, then the temperature of the motor can be anywhere. So it's a kind of compromise here, what we say. And we have one more thing. If the current is too big that goes into this thermal model, since this is just an approximation of the real situation. So if we have a fault current, or if we have a very long, heavy startup current, and before the motor was already running, so there is already a temperature, we could have an overfunction. That means during the startup, this here would go over the 100% and trip, because we consider a high current here. In order not to do that, we have the possibility to limit the current which goes into this model here. Practical value is something like 2 times of the nominal current here. Then only this limited current will be considered. Or we have also the possibility to freeze that thermal image under these conditions completely. So I would select current limiting, so it will go a little bit with the current, but it will not take the complete current in consideration here. Okay. And then we have the story with the ambient temperature. I have a setting for the minimum ambient temperature. You see minus 20 degrees Celsius. So if the temperature sensor measures suddenly minus 50 degrees, I don't want to have this additional leeway for the motor temperature, then maybe I have rather a problem with the sensor, which I don't detect. Then I can limit this and say, okay, less than whatever is the value, 0 degrees, or depending where you are. I don't want to use the complete possible range, which is there theoretically. Then I have the temperature rise at I rated. So this I need if I have a different ambient temperature than the 40 degrees, or if I use the current, the temperature sensor. If not, then this has no meaning, this setting here, just to mention that, because sometimes people don't know what to do here in that case. Okay, and this is our standard ambient temperature called default temperature, but it refers to the ambient temperature here. And this is basically, these are the settings. I was a little bit in a rush at the end for the, let's say, not core settings here of this function, but I think I could bring to you the basic idea for the core function, the thermal model we have, and the overload protection of the stator, which we also use for other means, transformers, cables, and so on. Next time, if you like, I will talk about the protection of the rotor. We use a similar model here, but the input data is different, which we can get from the motor manufacturer, so it remains interesting, I would say. Okay, here's a list of signals and measured values. I just put it here for the time being, a small documentation of the most important signals and also the most important measurement values which we have here in our system: time until trip, time until close, and the equivalent current, basically. So these are 3 measurement values which have some certain meaning here in this function, and I described this here a little bit on that slide as a summary to, let's say, to what we have as settings, so to complement the whole story here. And I think with that, I'm at the end of the stator overload protection function and the thermal model. Now the question is, do we have some questions still?
Yes, we do still have some questions. And the question is, how many of them will we answer? And I think at least
offline
2 or 3. And the rest will receive an offline answer. Exactly. So GG wants to know how to solve the problem of the appearance of the third harmonic current, that's around 150 Hertz, through the start point of a directly grounded synchronous generator.
This has nothing to do with motor protection
motors.
First.
I mean, a generator.
Give me a little bit time to think about that. I'm now in my thermal model, so I have to understand what it means.
First complicated question. Then the next
But
one.
I will try to find an answer. Yeah.
Homework.
Check that.
And then JW wants to know, is there also an example for a motor which starts with a Korndorfer starter?
Yes, this brings me to another point. We have a brochure, or we call that motor protection application guide. It's 84 pure pages and a little bit side dish around, let's say, like the front page and some editorial. Pure information about motor protection, and there's also one example with a Korndorfer starter. Basically, it's for those who don't know that, it's an auto transformer. So we have basically 3 currents which we can measure for the differential protection, and you know, we have the flexibility. I add a little bit hardware, then I have also a third current transformer, and then I make the differential protection over all 3 transformers, and I get a perfectly tuned differential protection. I don't need to deal with 2 current inputs only, and then have as such a inherent differential current coming from the third current, which is missing. So this is a very good example for the flexibility we have with Ciprotec 5 relays, and you find it in this application guide. I did not bring it here. You see the time is too much in 2 hours.
We will deliver the link to download.
We will deliver the link, for this motor brochure. I just put it in our CEOS database system just yesterday, because we had the last corrections of that application guide, and here you find additional information. So this was just a short extract of what we present you in this application guide. So it is worth to have a look inside there, I would say.
Thanks.
Okay.
So I think that's enough information for today. There is another webinar or another tutorial to come around motor protection. So thanks a lot for your participation. Thanks for staying with us this long in this webinar. It was planned shorter, but that was a lot of information. Thanks you, Klaus, for sharing that with us. And so I hope to see you in one of the next webinars. I think you might already receive the invitation for May the 2nd. If you want to learn something more around Siemens, join us on Hannover Messe in the middle of April, or join our other webinars. We have another one tomorrow, I think the week after. So I think just join us or visit us in our webinars webpage and pick out all the topics you like to see. So keep protected, protect your assets, and see you next time. Goodbye.
Goodbye. And think about, buy a lot of motor protection relays from me. Okay.